Hello. So in this video, I want to talk about the connection between the lengths of a 45, 45, 90 right triangle and a 30, 60, 90 right triangle to the coordinates on the unit circle. So what I will say is if the unit circle makes sense to you, you know where the coordinates come from, then you probably don't need to watch this video. But this video is intended to really drill down and hopefully help you understand where the connections are. Okay? So, if we start with a unit circle, and remember unit means a unit of one, it can be one anything, 1 mile, 1 inch, 1 kilometer. So the radius is 1, and if I were to start trying to label this, since I know that the radius is 1, I can certainly at least label the outside quarter points here, 1, 0, 0, 1, negative 1, 0, and 0, negative 1. But the question comes in, how do I start labeling these rotations here with these coordinates? How do I do that? Those in the middle. So that's what we're going to talk about. Now, in another video, I have this what I call the derivation of the lengths of the 45, 45, 90, and then later the 30, 60, 90 triangle in more detail in another video. So here I've got it written out and we're going to go through it. But essentially you start out and you say, well, let's assume I have a 45, 45, 90 right triangle where the hypotenuse, which will end up being the radius, which is always across from the 90-degree angle, that is a length of 1. Now what happens is, because I know these are both 45 degrees, then they must form sides of the same length. So this 45-degree angle forms this side, and this 45-degree angle forms this side, and they must be of the same length. So I label them the same way. If one's x, then the other one's also x. And then I use the Pythagorean Theorem and say, well, a squared plus b squared is c squared, but I'm plugging in x squared plus x squared equals 1 squared. And then I collect the 2x squared, they're like terms, so I have 2 of them equal to 1. X squared equals a half when I divide by 2. And then I keep going. I want to go ahead and take the square root of both sides. The square root of x squared is the absolute value of x. So now I have to remove the absolute value because basically I don't know if x was positive or negative. When it got squared, it became positive, but it could have been negative or it could have been positive. So that means x itself is positive or negative, square root 1/2. And then you're just simplifying here, square root 1 over square root 2. Obviously the square root of 1 is 1. So some books will use 1 over square root 2, or a lot of books will go ahead and rationalize the square root 2 in the denominator by multiplying by 1 here, square root 2 over square root 2, and now you'll get square root 2 over 2. So this is the triangle you'd get. Now, how do I work with this on the unit circle? Well, let's go back here. We're saying this is a 45-degree triangle, so if I were to take a 45-degree triangle, and the angle, well, right triangle where both angles are 45 and then you've got the right angle, and I put it over the unit circle, this is what I would get. And I know that across from each 45-degree angle is square root 2 over 2, that's the length. So that means that, in essence, when I'm talking about this point right here, so I'm talking about this point right there, that means I move in the x direction, square root 2 over 2, and in the y direction, up square root 2 over 2, and that's how I would plot that point. Okay? So what I mean by that is, if I had a grid, if I had an xy axis and I were to place it on top of the unit circle, right, then basically what I would do is I'd say, hey, well, square root 2 over 2 is about, well, it's this really long, but if I were to approximate 0.71, so then what I would do is, here I have a circle, and what I'm doing is saying, well, this is the graph paper I'm working with, and I'm letting each one of these little squares be 0.1, so when I have 10 of them, I have a total of 1, and since I said I had a unit circle, then the radius is 1. So now if I were to go literally and count and say, okay, I'm going to go square root 2 over 2, which I'm going to approximate as 0.71. So I'm going to plot, if I were to plot square root 2 over 2, comma, square root 2 over 2, I would plot it as 0.71, comma, 0.71. So in the x and the y, both in the same direction. In each direction, I'm sorry, it would be 0.701. So I'd go 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, and just a little more than that. And then 1, 2, 3, 4, 5, 6, 7. I'm a little off because I freehanded, I drew this circle freehand. But that would be it. And so what I would say is that this here is a 45-degree angle, and it has coordinates 0.71, 0.71 in approximation, or we would write square root 2 over 2, square root 2 over 2. Okay? And then, if we want to continue, we would say, well, let's say we did this with a 30, 60, 90 triangle. And let me get these pages set up for you. So we would say, okay, now this one, to derive that, what we do is we can't really do what we did before where we just start with a 45, 45, 90. Instead, we start with an equilateral triangle, which means that all sides, laterals, are the same distance, are the same length. So we choose them to be 1 because we have a unit circle and we want a radius of 1. But if all the sides are the same length, that means they're formed by angles that are the same measure. So 60, 60, 60, because 180 divided by 3 is 60. But here's the thing. We're trying to actually work with a right triangle, because it's the right triangles that represent the angles, right? The reference right triangles. So what do we do to get around this? Well, we drop a perpendicular bisector. And so what that does is it exactly splits the 60 degrees in half, so that you have 30 degrees and 30 degrees. And then it also splits the side that's 1 into exact lengths, half and a half. Now, I don't really need both triangles, so I only need to work with one of them. So let's say I pick this one, and I write down what I know about it. I have 1, 30 degrees, 60 degrees. I know this side is a half. What I don't know is this side right here, this perpendicular bisector. What is the length? Well, it's the only thing I don't know. It is a right triangle, so I can use the Pythagorean Theorem again, and I go through it all. So a squared plus b squared equals c squared. Remember, what I know is that a half squared plus x squared equals 1 squared. So now I actually do the arithmetic. A fourth plus x squared equals 1. I subtract a fourth from both sides, and now I'm left with x squared equals 1 minus a fourth. When you do the arithmetic, you get 3/4. So now I have x squared equals 3/4, take the square root of both sides, I get the absolute value of x. And so then when I remove the absolute value of x, I get plus or minus square root 3 over 4, but that's really square root 3 over square root 4, and I can simplify the square root 4 to a 2. So now x is plus or minus square root 3 over 2, and again, it depends on what quadrant you're in is really the reason it's plus or minus. Okay, so that's how we're using it. So now what that means is, I have my unit circle, and I'm like, well, how do I use this? Well, we just said, let's take a look here. Try one more. That now what we know is across from the 60-degree angle is the side of length square root 3 over 2, and across from the 30-degree angle is the side of length 1/2, and then the hypotenuse or the radius is 1. So how do I use that? Well, I take my triangle that's 30, 60, 90, and right here I put it on there. So what I know is across from the 30 is a half, but that's going to be my y coordinate, right? Because I'm moving vertically. And then across from the 60-degree angle is the square root 3 over 2, and that's going to be my x, because when I plot a point, I always start at the origin, and then I move over x and up y. So basically I'm going to have, for the 30 degrees, I have square root 3 over 2 and a half as my coordinates. Now, I can do the same thing for the 60 degree, right? Like that. And again, across from the 30 is a half, across from the 60 is square root 3 over 2, right? It's a bigger angle, it forms a bigger side. And how much do I move in the x, how much do I move in the y to arrive at this point once I start at the origin? And so I get over a half up square root 3 over 2. So that's how you actually come up with these coordinates, all right? Now, just so you can foreshadow this a little bit, remember, if I have a triangle here, if I just flip this, right, I just reflect this, it's the same triangle. So these coordinates actually apply for the whatever measure this is, which is basically 180 minus 30, it's 150. So it's going to have the same coordinates, right, square root 3 over 2 in the x and a half in the y. It's just that the x is negative and the y is positive. And if I were to take this and move it this way, right, then I'd have x is negative square root 3 over 2, and y is negative a half. That's how I'd get these coordinates, and so on and so forth. You can play around with that. And again, what I could do is, if I were to superimpose, right, a graph on here, right, and I were to say this is when I have a grid on top of my circle, the square root 3 over 2 is about 0.87 when you kind of simplify it. And of course, a half is just 0.5. So if I were to plot square root 3 over 2 comma a half, so xy, I'd plot 0.87 in the x and 0.5 in the y. So I would say 0.1, 2, 3, 4, 5, 6, 7, 8.6 or something like that. I'm sorry, 0.87. And then a half, so 1, 2, 3, 4, 5. And I'm a little off again because it's just a freehand circle. But you could see that's, if it were really accurate, that's what I would have. I would have, here's where my circle is, right there. So that's what these coordinates, when we say xy coordinates for these different rotations, that's what we mean. And so another piece of that then is to put it together when we try to find out, okay, how do we put all this together? Well, we divided the circle into 8ths and then 12ths. And I'll talk about why did we do that. But let's go through this really quickly. So if usually when you start with the x and y coordinate here on the circle, that's already dividing the circle into 4ths. I now want to divide those 4ths in half. So a 4th times a half is an 8th. So there you go, 1, 2, 3, 4, 5, 6, 7, 8. And basically you're dividing the whole revolution, which is either 360 or 2 pi, in 8ths. So you get either 45 degrees or pi over 4. And so basically what you're doing is you're starting here, and you're just adding 45 degrees or pi over 4 each time. So I add another 45 degrees or pi over 4, add another 45 degrees or pi over 4. So if I do that, then you can see the arithmetic, and you can see that I start at 0, I go to 45, add another 45, I get 90, add another 45 to 90, you get 135, and so on and so forth, till you go all the way around. Or if you do this with the pi's, you have 0 plus pi over 4 is pi over 4, then you take this pi over 4 plus another pi over 4 is 2 pi over 4, which reduced is pi over 2, but the 2 pi over 4 plus another pi over 4 is 3 pi over 4, 3 pi over 4 plus pi over 4 is 4 pi over 4 or pi, and so on and so forth. So these are the values you'll get going all the way around. You could also divide into 12ths. Well, that would mean you start with I go ahead and start with my circle, divide it in 4ths, but I want to divide each of those 4ths into thirds, right? So take this quadrant and divide it into thirds, and you'll get 12ths. So you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And using the same thinking, full revolution divided into 12ths is 30 degrees, or 2 pi divided by 12 is pi over 6. And so if you keep adding pi over 6, or you keep adding 30 degrees, you get all the way around. And I just want to mention here that what happens is the values for the rotations close to the y-axis end up reducing to pi over 3s, right? So if you look at these here, this square right here, right? That's how you'll sometimes see it. These are the pi over 3s versus these here close to the x-axis right here. When you reduce these are pi over 6s. So what you'll see then is pi over 6. This one ends up being 2 pi over 6, but it reduces to pi over 3. Right? Now you have 4 pi over 6, but it reduces to 2 pi over 3. So the ones close to the y-axis are the pi over, basically the thirds, right? Ends up reducing to some pi over 3. And the ones close to the x-axis reduce to pi over 6, right? So you'll see that little pattern that might help you memorize. I just count. So I go pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, 12 pi over 6, which should also be in there. Right? And so that's how I go around the circle, and then I just reduce. So I actually find that easier to memorize, but that's okay. It's however is easier for you. Right? Until in the end, you get the entire complete unit circle. And so hopefully that makes sense. And let me just address, why is it that we have these specific rotational values and not others? Well, if you remember what we did when we derived, you know, we said, oh, let's start with a right triangle and we'll have 45 degrees here and 45 degrees here. Well, that allowed me to say this is x and this is x, right, when that's 1. And that was absolutely necessary for me to be able to actually get an answer from the Pythagorean theorem. If I had said even something just slightly different, like, well, I'm going to let this be 46 degrees and let this be 44 degrees, you know, 1 degree more, 1 degree less. Well, now all of a sudden, even though I could say the radius or hypotenuse is 1, I can't say what this is. I can't say, even if I call it x, right? I can't say how this side is related to this side. I can't do what I did up here. So it does me no good. I really can't go anywhere. And that's true of almost all the other angles that I could come up with. And same thing is true when you're talking about the equilateral triangle. Right? When you started out and you said 60, 60, 60, well, that was awesome because when you came down here and you bisected it was 30 and 30. Well, what if instead you tried to do something like 60, 60, 60, and you're like, well, let me see if I can get, instead of 30, let me get 31. And I'm obviously exaggerating this, but, well, that's just, even if I did get that, then this is no longer a what? A right triangle. It's no longer a right triangle. So you're like, well, I can't work with it. I can't even use the Pythagorean theorem because it only applies to right triangles. So that's why we kind of got stuck with just those few reference angles that we know about, multiples of 30, 45, and 60 degrees and so on, because we really couldn't prove anything else. So everything else that we came up with, we had to come up with a different way. All right? Thanks so much for listening.